Hey there, welcome back to 2241. This is our examples 3.1 video on multivariable functions. All right, so our first problem says that we're going to have to compute and sketch a few things. So the values of two different functions given below and their domains and not their ranges. Okay, so just the domains. So we want to compute these two values. So first off, f of 2 or 3, 2. Well, this means wherever I see x, I plug in 3, and wherever I see y, I plug in 2. So we have square root of 3 plus 2 plus 1 over 3 minus 1. That is the square root of 6 divided by 2. And I think we can maybe rewrite that as the square root of 3 over 2. Yeah. Okay. And so that's the value of f at 3, 2. Next, we have g. The value of g at 3, 2 is, all right, we have 3 log 3 squared minus 2. All right, that's going to give us 3 times the natural log of 9 minus 2 is 7. All right, so nothing particularly special there. We just have two variables to keep track of, and we need to make sure that we plug things into the right places. All right, so what about domains? Well, domains are a little bit trickier because we have to worry about some more stuff here. So we still have the same three things to worry about. Bad for domains. We have 1 over 0. We have square root of a negative number, and we have natural logs of non-positive numbers. So these three things are what we want to look out for when we're trying to compute domains of multivariable functions. All right, so now if I look at f and I say, all right, do I have any possibility for 1 over 0? Yes, I do, where the denominator here is equal to 0. So for the domain of f, I want to look at, okay, solving the equation x minus 1 equals 0, because that would force the denominator be equal to 0. And this says, all right, all of the places where x equals 1. Okay, so the places where x equals 1 are bad. I don't want those, right? What else do I have? Well, I've got this square root here, and I want this to be non-negative. So this has to be positive in order for my function to exist. All right, so that means that I want x plus y plus 1 to be, or not positive, non-negative, because it can also be 0. And now, if I set this equal right here, then you can see that's the equation of a line in 2 dimensions. And so this is the equation of, or the inequality for the space above or below a line. And we'll just check and see what that is. So y is greater than or equal to minus x minus 1. So y-intercept of minus 1 and a slope of minus 1. Okay, and so that's what we can write in for our domain. It's the set of all x, y in R2 so that x is not equal to 1. Remember, this was good and this was bad. So I want x to not be equal to 1. And y is greater than or equal to negative x minus 1. Okay, so that's the domain of f. Now, to compute the domain of g, we do the same sort of thing. We just check, do we have any of these three options for things that can go wrong with domains? So we don't have 1 over 0 occurring. We don't have square roots of negative numbers anywhere because there are no square roots in this function. But we do have a natural log, and so we want to make sure that the input to that natural log is always a positive number. Now we check, all right, x squared minus y needs to be strictly greater than 0. All right, well, that means that y needs to be less than x squared. And so these are, again, good values. Y being greater than or equal to x squared are bad values. And so this is how we can write the domain, is the set of all pairs x comma y in R2 such that x or y is less than x squared. You can also use the complement x, y in R2 so that y is not greater than or equal to x squared. Okay, so that's how to compute values of functions and domains. Right. So now, what's our next problem? It says use the table to estimate the wind chill index W when the temperature is minus 12 degrees C and the wind speed is 23 kilometers per hour. All right, so let's have a look at this table over here. So we have the wind chill index as a function of air temperature and wind speed here. So temperature T along the rows and speed along the columns. So let's see, it says minus 12 C, and that's going to be between negative 10 and 15. So between these two rows, and 23 kilometers per hour. So here's 20 and 25, and between these two columns. So we've got these two rows and these two columns. That's going to be in this block of 4. And we want to estimate using the values that we're given. All right, so 12 is about 2/5 of the way between 10 and 15. And so we're looking at about 2/5 of the way between 18 and 24, or 2/5 of the way between 19 and 25. So let's do that. So, whoop, come on, sorry about that. So 2/5, where did that 2/5 come from? Well, 12 is 12 minus 10 and 15 minus 10. The distance between 12 as a proportion of the distance between 15 and 10 is 2/5. And that's where that 2/5 came from. Okay, and so this is the proportion that I need for 18 and 24. All right, so what is 2/5 of the distance between 18 and 24? So we take the difference of those two, and we get, let's see, that is 6. So 2/5 times 6 equals 12/5. And that's what we want to add on to 18. Okay, 18 times 5 is 90. We have 90 plus 12 is 102/5. Or maybe it would be easier to write this as a mixed fraction. We have 2, so 20.4, I believe. Okay, so that's our lower estimate. And now we have in the second column 19 and 25. So now I need 2/5 of the way between 19 and 25. Okay, so 2/5 of 25 minus 19. Okay, this is also going to be 6. So we have 12/5 again. And we want to look at 19 plus 12/5. Okay, we'll add 2 to that, and we get 21.4. Okay, so we have 20.4 and 21.4 as our lower and upper estimates. And that was just taking into account the temperature at 2 different wind speeds. And now I want to look at when the wind speed is between those two values, 23. So now I want to know what proportion of the way between 20 and 30 is 23, or sorry, 20 and 25. 20 and 25. So where does 23 go? So we have 23 minus 20 over 25 minus 20. And this is 3/5. Okay, so 3/5 of the way between 20 and 25. And now I want to look at what is 3/5 of the way between 20 and 21. So 3/5 of 21.4 minus 20.4. So the 0.4 cancels out, we just get 1. And so 3/5 of that is 3/5. Okay, so our temperature, or wind chill estimate should be 20.4 plus 3/5. All right, well, 3/5 is 0.6. So our estimate should be exactly 21. And so remember, this is minus 21 degrees Celsius. Oh, no, sorry, that's incorrect. 21 is our wind chill index, is our estimate for that. So that would be a number appropriately in between here and here, or here and here. Right. So this is a two-variable function with just a bunch of discrete values listed out. And this is one way that functions can be listed. All right, next problem. Given this function, square root 9 minus x squared minus y squared, compute the domain of G and the range of G. All right, well, domain, we've seen that before. We look for 1/0 square roots or logs. We have a square root here, so we want to be careful with that. And that means that we want 9 minus x squared minus y squared to be non-negative. All right, well, if I solve that, it means x squared plus y squared is less than or equal to 9. Solve for x squared plus y squared. And this is the equation of a circle. It's a circle. And it's the inside of a circle in the xy plane. So if I were to graph my xy axes and then draw a circle, that's not a circle, it's an ellipse. There we go. Say, all right, this is radius 3. Then all of my domain values are inside of the circle, inside and on the circle. So all of that's okay. All of this is bad. Can't plug in anything outside of the circle to this function. All right, so the domain, just like before, domain, that's thicker, of G is all of the x, y pairs, so that our x squared plus y squared is less equal to 9. Sometimes we get a little lazy and we'll just write this with the equation, and we'll take all of the other stuff as being understood. But we need to use the brackets to ensure that we're talking about a set here. Okay, so what about the range of this function? Well, we're looking at a square root function, and all we really need to know is, does this achieve the minimum and maximum possible values? It doesn't achieve the maximum possible value for a square root, but it does achieve the minimum. So I can take x equal 0 and y equal 3, and then we get G of 0, 3 is square root of 9 minus 9 is 0. Okay, so I can achieve the minimum possible value for a square root at 0, 3 right here. What about the maximum possible value? Well, that's going to be where I subtract the least from here, and that would be 0, 0. So g of 0, 0 is square root of 9 is 3. Okay, so my maximum possible value is 3, and my min is 0. All right, and then my range is just everything that happens in between those two, because this is a continuous function, so it achieves all of those values in between the max and the min. All right, and that's by the intermediate value theorem, by the way. Okay. So next problem, we want to sketch the graph of f in R3 for this function. Okay, we can see that this is a polynomial and it's linear because it only has x and y to the first power plus a constant. So the easiest way to do this is to reduce it to something we already know, the equations of planes. So z equals 6 minus 3x minus 2y. Z is just the name for the output variable. And if we solve this for the constant on one side, we have z plus 3x. Actually, let's put the z on the last bit. So 3x plus 2y plus z equals 6. Okay. And now we just need a vector in that the graph of f. So let's pick x equals 0, y equal 0, and that's going to imply that z equals 6. All right, and then we recognize this as the graph of a plane with normal vector 3, 2, 1. Okay, and now we can go ahead and graph our plane in 3 dimensions. Our normal vector is pointing in the positive direction for every one of these axes. It is pointing in the direction 3, 2, 1, sort of like that. Let's find our x and y values as well. So if x equals 0 and z equals 0, then y equals 3. And if y equals 0 and z equals 0, then x equals 2. So 2 right here, 3 right here, and now it's kind of a little bit easier to draw my plane. All right, so the perspective might be slightly off, but that's kind of the idea right there, is that our vector should be going perpendicular to this plane. And so the surface itself is just going to be an extension of that triangle, sort of like this. Okay. And there we go. That's a rough sketch of the graph of f here. All right. Next up, we have another sketch, g from 3. So g of xy is square root 9 minus x squared minus y squared. Okay, so we already know what the domain of this function looks like. And now I want to sketch its graph. So again, I'm going to need some axes here. So here are my axes, x and y. And then I need a z-axis, of course. We'll go ahead and label those. X, Y, Z. And then I have a circle in the plane as my domain. So I computed that back in problem 3. So, yeah, that's fine. And we know that the maximum value of g was 3, and it happened right at 0. So g max equals 3, and that was g of 0, 0. And we have this point right about there. And if we go ahead and do the same sort of thing that we did for f in problem 4 with g, z equals square root of, we can go ahead and square both sides and add x and y to the other side of this equation. Then we get x squared plus y squared plus z squared equals 9. And you probably recognize this as a quadric surface. It is an ellipsoid where all of the radii are the same. And so we have a sphere in the x, y, z space. There's our sphere in the x, y, z space. So it's just the top half, again, because we have the square root here. If we put a minus square root, we get the bottom half. And this is the graph of G. Okay, so that's it for this example video, and then we'll follow it up in examples 2.